So let's talk a little bit about what we learned from stability and convergence analysis. First of all, we learned that when we define the mesh, the spectral radius of convergence increases and it asymptotically goes towards 1 if the method is stable. Okay, if the method is unstable already, then it's a different issue. Eigenvalues are already greater than 1, and then we don't even bother about mesh refinement and all that. But if the method is stable, we found the eigenvalues go towards 1 as we define the mesh. We also found that the condition number increases with mesh refinement, and so the convergence gets slower. Okay, and the most important thing we found was that the component, when we do this Fourier decomposition, the component of the error that's primarily responsible for slow convergence are the large wavelength components. Okay, it's not really just one component, but we can say the large wavelength components or the small frequency components. Okay, so from that, this whole idea of multigrid methods developed. Okay, so people clearly saw that, well, when we do the solution on a coarse mesh, the convergence is very fast. When we do the solution on a fine mesh, convergence is slow. And then they came out with the idea that, okay, can we somehow mix these two to accelerate the convergence? Okay, that's the basic idea. Now there are two types of multigrid methods. The more primitive one that was first developed is the geometric multigrid, and then of late, especially with the advent of unstructured mesh, people have gone more and more towards algebraic multigrid. Okay, so most commercial CFD codes, for example, now have the algebraic multigrid method as almost the default method for solving linear systems. Okay, now whatever multigrid method we are talking about here is for the linear system. Okay, there is another method called the nonlinear multigrid method, which is also sometimes known as FAS, or full approximation scheme. That's what the multigrid people or the community calls it. Okay, that is for solving nonlinear algebraic equations on a grid iteratively and then getting fast convergence. Okay, but here we are talking about really the multigrid method for linear systems, which has been our theme for a long time now. Okay, any questions? So the geometric multigrid method basically makes use of two or more multiple mesh levels. Okay, actual physical meshes. All right. Whereas in the algebraic multigrid method, it sort of uses this idea, but it doesn't really use a mesh per se. Okay, it starts working from the point where you've already assembled the full matrix for the finest mesh, and then it takes those equations and does certain things to it to kind of mimic what would happen on a coarse mesh. Okay, we'll after we finish geometric multigrid, it's a little bit more complicated. Okay, but of course it has its advantages because you don't have to use multiple meshes. So let's talk about the geometric multigrid. What's the basic philosophy? Okay, so the basic philosophy is to use a coarse mesh or several levels of coarse mesh to damp out the low frequency error components preferentially, in a sense. Okay, because we know that that's what's holding up convergence. And if you think about it physically, then we know that the coarse mesh allows propagation of information very quickly through the mesh. So for example, here's a simple example of a heat conduction problem. Okay, so if you are, let's say, doing Gauss-Seidel iterations from left to right, okay, and you start off with, so I've color coded it just to show that, okay, the orange is hot and the blue is cold, and any color in between is a mixture of the two. Okay, so if you start with all blue and then you start solving this problem, okay, as you know, Gauss-Seidel iteration, it's a pointwise method. So what's going to happen is with iterations, you're going to get a tiny bit here hot Then next iteration, the information is going to again propagate a little bit forward. Next iteration, a little bit forward. And you're going to need several thousand iterations before all of this become a mixture of red and blue. Okay, that's what's happening in the fine mesh, essentially. Now think of it this way. If I had just a few mesh points, 4 mesh points, okay, then if you solve the same problem, you would, first iteration, this would already get colored. Second iteration, that would get colored. Third iteration, that would get colored, and so on. Okay, so the information propagates very quickly with iterations. Now the answer that you're going to get is not very accurate, but it's still a pretty good semblance of what the actual answer should be. Okay, so from a physical standpoint, if we think about multigrid, basically the idea of using a coarse grid is to make the information propagate through the domain very quickly. Okay, and somehow then use that to get faster or accelerated convergence on the fine mesh itself. Okay, so that's the general philosophy. So I already explained this, that if you use a coarse mesh, it would take very few iterations for the information to propagate through the mesh. Okay. So here are some important points to note before we actually start constructing a multigrid algorithm. First important point is that the final solution must be obtained on the finest mesh. Okay. Any other solution is an unacceptable solution. You can use that solution to accelerate convergence, but you can't use that solution as the final solution that you're interested in. It's a solution laden with large truncation errors. Okay, so we can't use that solution. We can only use it for convergence acceleration. So coarse mesh is used only to accelerate convergence, not to obtain final mesh. Okay, final solution. Now, if you use, let's say, 2 levels, and we are going to talk a lot about a 2-grid multigrid. Okay, because the true multigrid is a little bit more complex, okay, but we will actually talk about the full algorithm for a 2-grid multigrid, and that's what you're going to implement for your homework, just to get an idea of how it works. Okay, so in the 2-grid multigrid, what happens is the accuracy, of course, is the same as the fine mesh. Okay, convergence will be between that of the fine mesh and the coarse mesh if only one sweep at each level is used. Okay, and we'll get to that in a moment, what exactly happens there. Okay, if you use additional coarse mesh sweeps, then convergence can be actually better than the coarse mesh solution. So if you think about your convergence plots, okay, let me just go up here and blank this and plot this. So if you think about your convergence plots, fine mesh, you got this. Coarse mesh, you got that. Multigrid solution is going to be somewhere in between if you use one sweep of the coarse mesh. But we're saying if you use multiple sweeps of the coarse mesh, this could actually go beyond that. Okay, which is really remarkable if you come to think of it. I mean, even getting it here with just 2 coarse mesh levels is quite remarkable. Okay, but we'll see what happens with that as we move along. All right, any questions so far? Okay, so here is how the 2 mesh level works. Now I'm calling it a V cycle. I'll explain that later on what it exactly means. Okay, for now just ignore that. So first thing is you set up both the fine mesh and the coarse mesh, and I'm in my presentation I've color coded it, so the fine is red and the coarse is blue. Okay, so here's what your mesh arrangement will look like. So at the intersection of all red lines you have a fine mesh node. Okay, and at the intersection of all blue lines you have a coarse mesh node. Now you can see here there are certain points where, for example, you have the coarse and the fine mesh co-located. Obviously every point has a fine mesh node, but at alternate points you also have a coarse mesh node, so they are co-located, while there are other points where you just have a fine mesh node. Okay, This is pretty easy to imagine and construct for a regular Cartesian grid like this. If the grid becomes let's say curvilinear or of different shape, then it's not as easily done. There's a lot of bookkeeping to be done. Okay, but it's fairly easy to understand when you have something like this. Okay. Any questions so far on what we have here? Okay, so now here I have denoted these nodes by indices that you're familiar with, I and j. I'm using small letters for fine mesh nodes and capital letters for coarse mesh nodes. Okay, so for example, if you think about the central node right here, okay, that has an index small I comma j, that's a fine mesh index, and then there is also a capital I comma j. Similarly, the one here is I plus 2 comma j for the fine mesh, but I plus 1 comma j for the coarse mesh, okay, and so on. Now there is a relationship between the small indices and the capital letter indices, or the fine and the coarse mesh, and that's given by, let's see here. So those are your mesh spacings. You know that already. So now we have a delta xc and a delta xf, standing for coarse and fine. And here is the relationship between the coarse and the fine mesh indices. So small I is equal to 2 capital I minus 1, and small j is 2 capital J minus 1. So if you start here, for example, okay, right here in this corner, let me use black so I don't confuse you. Right there, that's capital I equal to 1 and capital J equal to 1, because there's a coarse mesh node there. Okay, so if you compute this using this formula right there, you get 2 times 1 minus 1, which also gives you a 1 comma 1. So that node is 1 comma 1 for both the coarse mesh and the fine mesh. Okay, by the time you get here, okay, this will be 2 comma 1 for the coarse mesh, but now if you plug in here, you get 4 minus 1, 3 for the I and 1 for the J. So you get 3 comma 1 for the fine mesh. Okay, so as you can see, this index automatically takes care of the numbering system. So if you use the coarse mesh numbers, you can automatically calculate corresponding fine mesh numbers from this relationship. Okay, any questions on that? All right, so that's our mesh, and grid spacing I already talked about. That's pretty straightforward. Okay, so setting up of the mesh is done. Now it's time to solve the equation. So step 2, what we are doing is we solve to partial convergence the governing equations of the fine mesh using a solver of choice. Okay, now why partial convergence? Well, so suppose you use Gauss-Seidel as the solver. If you take it to full convergence, you're going to need whatever 30 or 60,000 iterations that you got for the 81 by 81 mesh, let's say. Okay, it doesn't serve any purpose. What we're trying to do is accelerate convergence. So what we will do is we will only partially converge the solution. Okay, that partial solution will have some error from the exact solution. Okay, that's the epsilon we have been using in our stability analysis. Then what we'll do is we will take that error, transfer it to the coarse mesh, okay, and do something with it before we pass it back again to the fine mesh. All right, so that's the idea, that we use partial convergence, because solving to full convergence would defeat the purpose of the whole multigrid algorithm, because it's slow to begin with and we don't want to go that route. So second question is, what solver should I use? Okay, any of the solvers we have studied thus far would be acceptable. Okay, however, it is best to use one that has least computational cost per iteration and is easy to use. Why? Because we only want to solve the equations partially. So why use a fancy solver? Okay, we're just going to solve it reduce the error a little bit and then get off that track. So, there's no point trying to use a fancy algorithm like conjugate gradient, because we are not going to go to full convergence anyway. Okay. Another thing is we want to look at the computational cost per iteration. If you use a fancy solver like conjugate gradient, the cost per iteration may be pretty high. Okay. Instead, we want to use one that's pretty cheap per iteration. All right. Gauss-Seidel is a great choice for that because there are many, many reasons. One is the computational cost per iteration is very cheap. Number two, it's very easy to use. Number three, it can be used for both structured and unstructured mesh. Okay, you don't have to really worry about your matrix structure at all. You don't even have to set up a matrix to be able to use Gauss-Seidel. Okay, so that's why it's very nice. The point being that the convergence acceleration in this case is really provided by the multigrid algorithm, not by the solver itself. So therefore, using a solver that's not highly convergent is still okay. All right. And as I said, it can be used both for structured and unstructured. So that's great. The solver that you use in step 2 to solve the equations on the fine mesh is often known as the smoother. Okay. The name smoother comes from the fact is because we are essentially smoothing out errors. Okay. Remember, when you start with your algorithm, you start with a guess for phi. So you take that phi, subtract it from the exact analytical solution. That's your starting error. What this solver is really doing is it's trying to drive that error to 0. Okay, that's why it's called the smoother. It's smoothing out the errors. Okay. Okay, now another question that we often face is, I mentioned here up on top that we go to partial convergence. So the question is, what exactly do you mean by partial convergence? Do you mean 2 orders of magnitude convergence, 2 iterations? What exactly does it mean? Okay. So in general purpose multigrid implementations, what people do is they solve the equations until the point the residuals drop by a factor of 2. Okay. So our final over our initial is half. After that, they quit. Okay. If you want to do it in a more simplistic way, you might say, well, I'm not even going to monitor the convergence and do all that. I'm simply going to just use 1 sweep or 2 sweeps of Gauss-Seidel and then be done with it. Okay. And that's fine too. It's just an unoptimized form of the solver if you do that. Okay. And even this criteria doesn't guarantee that this will give you, this criteria here doesn't guarantee that it will give you the best overall convergence. Okay. It's just something that people came up with as a rule of thumb. Okay. There is really no rule as to how far you should go down in convergence or how many sweeps you should do. Okay. So for the purposes of this class, I would say just perform 1 Gauss-Seidel sweep through the entire computational domain in this step. Okay. And you will actually find, if you are keen enough to fool around with this and really look for its performance characteristics, you will find that doing more than 1 sweep, even if you do 2 sweeps, it's not going to change your overall convergence too much. Okay. You'll just be spending extra CPU time. So ultimately, you always have to remember, whatever you do, the iteration count is not important. What's important is how much overall CPU time am I taking. Okay. If I do 5 sweeps here, I'm doing a lot of calculations then and spending time, but is it paying off in terms of the overall convergence? Okay. That's the question ultimately. So once we finish step 2, we have a partially converged solution, and that partially converged solution has an error. Okay, that error is this, or I think we called it P comma Q in 2D at the kth iteration. Okay, that's the difference between the solution. Once you get to the partial stage, 1 sweep of Gauss-Seidel, let's say, okay, you subtract it out from the exact analytical solution, or sorry, the exact numerical solution, and you have your error. Okay, that error, as you know, or we have found, is dominated by the lowest frequency component. Okay, Maybe dominated is not a good word, but that's the component that we know we have to somehow address. Okay, because otherwise this thing is going to just converge like the plain Gauss-Seidel, nothing better. All right. So therefore, we must now take steps to specifically damp out that error component so that the convergence can be improved. Okay, and how do we do that? Next step is we transfer that residual. Okay, we are calling it the error vector in this case, to the fine mesh. Okay, so what we are doing is, here is my residual that I've defined. Okay, so I've done one sweep of Gauss-Seidel. I have a solution. I calculate my residual vector. Okay, which you guys are doing in your Gauss-Seidel procedure anyway. Okay, you take that residual and now you're going to transfer it to the coarse mesh. Okay, so this is usually done via interpolation. However, in the setup that we are looking at, there is always a coarse mesh node on top of a fine mesh node. They're co-located. Okay, and therefore you don't really have to do any interpolation. All you have to do is just copy that data to, whatever array you are using for residuals for the coarse mesh. Okay, so when you are allocating memory, for example, your residual vector for the fine mesh has size NF times MF. Okay, you're just simply transferring that to another one, which is NC times MC, only the coarse mesh points, only the fine mesh points that sit atop the coarse mesh points. Okay, that's all we are doing. And that residual, we are now going to give it a new name. We're going to call it the residual on the coarse mesh that was transferred from the fine mesh. Okay, so that's the symbol we are using here to denote that. This is actually residual on the coarse mesh, but it wasn't calculated on the coarse mesh. It was calculated on the fine mesh and then transferred over. All right? Everybody get that? So that's step 3. Okay? So in this step, we have essentially prepared ourselves to use the coarse mesh to do something different to the fine mesh residual than the standard Gauss-Seidel would do. Okay? This step is also called the restriction step of the multigrid algorithm. Okay. All right. So now we've transferred the residual to the coarse mesh. Next, what we are going to do is we are going to solve to partial convergence the correction equation on the coarse mesh. This is called smoothing on the coarse mesh. Okay, smoothing of errors on the coarse mesh. That's what it's called. So here what I have is you've transferred this residual. If you recall, going back to several lectures ago, we talked about the correction form of equations. So what we said is, for example, in the Stone's method, we did not solve for A phi equal to Q. Instead, we recast this in correction form and we solved A times delta, delta being the correction of phi, is equal to R. Right? So that's what we are doing here. We're solving the equation on the coarse mesh in correction form, not in its original form. So we've transferred the residual, this right-hand side that you have here, and now this A matrix that you have here, this has elements that are calculated from the coarse mesh. Okay, so for example, that A matrix will have 1 over delta xc square in its, or 2 over delta xc square plus 2 over delta yc square in its diagonal, negative 1 over delta xc square in its off diagonals, and so forth. That's what this matrix is, the A with the superscript C. It's just the same A matrix that you normally calculate, except with the coarse mesh spacings. Okay? So when you solve this system, what it gives you is a correction of phi on the coarse mesh, only on the coarse mesh points. Okay? Not on the fine mesh points. I'll get back to the solution of this in the next slide in little more detail, but for now let's just say we know how to solve this. Okay? So the output is this guy on all the coarse mesh points. And as in step 2, we can use any solver, but we prefer to one that's simple and computationally inexpensive. And again, we use Gauss-Seidel here. Okay. Now, I want to make a point here that although Gauss-Seidel is the best method for reduction or for solution in step, it is not the best method in this step. Okay. In this step, ideally, we want a solver that completely drives the error down to 0 on the coarse mesh. Okay? So typically, you would want to do first, if you use Gauss-Seidel, you would want to do more sweeps of Gauss-Seidel than one. Okay? That's one thing. Of course, it'll incur additional computational cost if you do that. Or you would want to use a solver which basically gives you very fast convergence. Okay. Now I'll get to the multigrid algorithm where more than one mesh levels are used, and that's when I have some additional remarks on this, but we'll hold off until then. Okay. So it is, as I said, it is customary to use tighter tolerance or more sweeps in this case. This is because this step is meant to damp out the long wavelength errors completely. Get rid of them completely. So pictorially, if you think about it, if I plot error versus x, okay, this is the error of the fine mesh that I brought into the coarse mesh, right? That error may look something like that. Okay, what we are trying to do in this step is basically drive it down to 0. Okay, so that's the idea here, and that's why we need tighter tolerance here for this step. Okay, let's talk now a little bit about this equation. How do we solve that? Okay. So here's the Gauss-Seidel equation in correction form. Instead of writing it in matrix form, I've just written it as, so here's your diagonal, here's your off diagonals, okay, the 4 terms that you have, the east, west, north, south, and then here's your residual. Okay, you all are familiar with this now. So in the Gauss-Seidel iteration scheme, we would typically take 2 of these terms and transpose them over to the right hand side. Essentially 2 of these terms will be implicit and 2 of them will be explicit. Okay, that's what we do. Now what happens is, if you do, let's say, 1 sweep of Gauss-Seidel, you have to now solve this equation with some initial guess of phi prime, the correction, right? Just like you solve for your a phi equal to q, you start with some guess for phi and then you solve it. Okay, here instead you have to start with some guess for phi prime and then solve it. So the very first time you do it, you don't know what phi prime is. Okay, you're not carrying over its value from previous iterations and stuff like that. So the best case scenario is you assume that it's 0. All right, so essentially what it reduces to is this equation where this initial guess is 0, and therefore it completely drops out and you're left with that. It's basically the right hand side divided by the diagonal. That's all. Okay. Now if you are doing additional sweeps, then at that point you have a phi prime on all the nodes and you can use that. You can use the full equation in that case. Okay. Everybody understand this? So first iteration, since you don't have a guess, if you're setting up your solver in a way that you intend to do only 1 sweep of Gauss-Seidel in this step, then just use that equation. It's so much more simplified than using this. Why? Because remember, multiplication by 0 still counts as a multiplication. So if you implement this in your code, you will still be doing 5 multiplications in the numerator. Okay? If you implement this, you will be doing only 1 division. No multiplications at all. It will save you some time. All right. So if you're planning to do only 1 sweep, don't code this in, code this in instead. If you're planning to do more than 1 sweep, you might want to code in the full Gauss-Seidel. All right. Everybody with me? Okay. So as I said, the advantage of doing this over that is it saves 80% of CPU time in this step, because you're not doing all those multiplications, the A east times phi east plus A west times phi west and all those terms are not calculated at all. It's just one division. That's it. Okay, so let's just go back here. Previous page. So this was our step 5 where we solve for phi prime. Okay, that's our output, this guy. On the coarse mesh. So this is on the coarse mesh. Now, next step, step 6, what we do is we transfer that from the coarse mesh to the fine mesh. Back again. Remember earlier we had transferred the residuals from the fine mesh to the coarse mesh. Now we are transferring back the correction of phi from the coarse mesh to the fine mesh. Okay. Now, of course, this will require true interpolation because we have several scenarios. One is we have direct transfer. So wherever we have nodes sitting atop each other, coarse and fine, we just transfer the phi. That's it. Okay. You will run into scenarios like this where you will have a fine mesh node in between two coarse mesh nodes. So you will have to do a 2-point interpolation. Okay. Now with equal spaced meshes that you will typically use for your homework, all you have to do is you just have to do an average. Okay. It's 1/2 this plus 1/2 that. But in general, if that's not the case, you would have to do a distance weighted interpolation. Okay. Which is what people typically do for non-uniform mesh. You would also run into these kinds of scenarios where you would have a node, a fine mesh node, at the middle of 4 coarse mesh nodes, like that. Okay, so this scenario here is the same as what you have for these 4 nodes, but the middle one is a special case where you need a 4-point average. Okay, or a 4-point interpolation to transfer that information. Okay, so 3 types of transfer you will need. One is a direct transfer, the other is a 2-point interpolation, the other is a 4-point interpolation in this case. Okay, once you do that, and then just go over it carefully so that you're not doing the same thing for the same node twice. Okay, you got to kind of carefully go over your grid structure and see, make sure that you're doing it only once, that you're not repeating it unnecessarily. Okay, so once we have done this, then we have the phi prime on the fine mesh at all fine mesh nodes, even though it was not calculated on the fine mesh itself. Okay, it was calculated on the coarse mesh and then interpolated. But be that as it may, we do have fine mesh correction. Okay, what we do next is, so by the way, this is called the prolongation step in the multigrid algorithm. Okay, so there are 2 important steps, the restriction and the prolongation. The restriction is where you transfer the residual from the fine mesh to the coarse mesh. The prolongation is where you transfer back the correction of phi from the coarse mesh to the fine mesh. Okay. So a couple of programming tidbits. So let me just skip this. I'll get back to that in a moment. Okay, let's just finish the algorithm and then we'll get to that. So step 7 is, so you've gotten this now, this correction on the fine mesh, you add it to whatever fine mesh solution you had. Okay, that fine mesh solution that we are talking about here that you already had was what you got after one sweep of Gauss-Seidel on the fine mesh. Remember, that's when we stopped the Gauss-Seidel and deviated to the coarse mesh. And now we have come back to the same point. Okay, we're saying, okay, we had the solution already. Now we have a correction to that solution. We are going to add it to that. Okay. So as I say here, this is the solution we had at the end of step 2. So what we have done now completes one full iteration. All right. So we performed one sweep of Gauss-Seidel on the fine mesh and stopped. Instead, we passed the residual to the coarse mesh, and then we are bringing back the correction again. So what did this sequence of solutions really do to the error? That's the next question. I mean, fine, you're doing all this fancy stuff, all these acrobatics, but what did it really do to the error? Okay, that's the important question, and I'll show you some examples. Basically what it did was it took the residual error the error, and then it transferred it to the coarse grid and smoothed it. And in the process, the low frequency or large wavelength components got filtered out, essentially. Okay, and that leads to rapid convergence. Here is a schematic of what might have happened. Okay, this is not actual calculation. I'll show you actual data in a bit. So imagine that you're solving a one-dimensional problem using iterative method. Okay, and here's your coarse and fine mesh nodal arrangements, as you can see. 11 fine mesh nodes and 6 coarse mesh nodes. Okay. Now, after you've done one iteration of Gauss-Seidel, this is what your errors may look. Okay, you've started with some solution, it has some error. Okay, and you plot the error at every fine mesh node point. Of course, at the boundaries, if you have Dirichlet boundary conditions, the error is 0. But on all other points, you have some error, and that's what the error distribution may look like after one iteration of Gauss-Seidel on the fine mesh. Okay. Now what we do is we transfer this information to the coarse mesh. Okay. So what are we doing? We are selectively taking these points. That one, that one, that one. Wherever we have coarse mesh points, we are just selectively taking those errors, putting them on the coarse mesh. Okay. So this is the error distribution that we are getting on the coarse mesh. You already see that it's much lower than, most of the errors are lower than the errors that you had on the fine mesh. Now we are going to do further Gauss-Seidel on this, okay, the smoothing step on the coarse mesh, which is going to reduce these guys further, bring them closer to 0. Okay. So that's the whole idea of what's going on in the whole process of transferring information and then bringing it back. Let me show you an actual error distribution of that comes out from a computation. Okay, so here is a two-dimensional Poisson equation solution that we are looking at, similar to the one that you've been solving in your homework. And here is the Gauss-Seidel 161 by 161 mesh solution. It takes about, I guess, about 50,000 iterations or so, right here, the red curve. Okay, and then when you do two grid, 161 by 161 and 81 by 81, this is how many iterations it takes, about 5,000. Okay, dramatic reduction in the number of residuals, as you can see. Now, here is what happens to the errors, what I was talking about. So this picture that you see on the left, this is showing you a contour of the error after one Gauss-Seidel sweep on the fine mesh. Okay, so I started with a certain value of phi. I think I started with phi equal to 0 as the initial guess. Okay, and I did one sweep of Gauss-Seidel, and I think the peak values go to something like 250 or 300 in this problem, but you're seeing peak values of 35 and minus 20, which is about 10%. Okay, so if you compare the error to the exact solution and do a percentage error, it's about 10-20% error, and this is what the distribution of the error looks like. There are strong errors in the corners because there are strong gradients there. Okay, then what I do is I take that error. Okay, so here you can see it says convergence error after the Gauss-Seidel sweep, step 3 in the first iteration. Okay, and then here it says convergence error after the coarse grid correction, step 8 in the first iteration. So if you look at that, let's just go back to our algorithm once to look at what those steps were. So step 3 was solving on the fine mesh. Okay, so the left hand contour plot that I was showing you was after you do one sweep of solution of this equation. Actually it's step 2. The numbering on that write up is slightly different than here, but step 2 here. Okay, and then step 8 is or step 7 actually in this case, would be this part here. Okay, so you take that error that I was just showing you and you transfer it to the coarse mesh, you smooth it on the coarse mesh, add it back, and when you add it back, this is what the error distribution looks like. Okay, so one thing you see here is, I mean, this is not Fourier decomposed, this is just the error, so it's hard to say that what wavelengths got filtered out. Okay, you actually have to do a Fourier decomposition and look at it in spectral space to see what error distributions actually, or what error components spectrally got filtered out. Okay, but nevertheless it does show you. So you can see here I have maintained the same color map for both plots so that you can see what's going on. You can clearly see that these red colors that correspond to these peaks are not even hit here. So here you're down to about 20-25, something like that. And then again, the dark blue color doesn't even show up here. You know, you're down to somewhere about here. So the whole error spectrum shrunk to some extent. Okay, this is just what's happening in one iteration. Now, if you do this repeatedly, you can imagine what will happen. Okay, and the whole once you execute the whole algorithm, the end result is something like this, which is kind of remarkable if you think about it. 50,000 to 5,000, 10 times reduction in the number of residuals. Okay, and this is just a 2-grid algorithm, by the way. I'll show you some results for multigrid, true multigrid in a little bit. Okay, any questions on that?